Things just got a lot more interesting on the Sun over the last 24 hours. Remember this little alpha sunspot group that we were looking at over the last couple of days? Compared to region 2674 here, which is much larger. This region has increased in size over the last 24 hours by a little over 100 millionths of a solar hemisphere, which is pretty respectable, but it still is not that complex. If we look at the magnetic fields, we can see that the magnetic fields from this region are still primarily bipolar in nature, so that makes this a beta sunspot group. It lost its gamma configuration over the last 24 hours, as I said it probably would. And so it's still not really that complicated. It looks complicated, but it's really not that complex. What is complex, or rapidly becoming complex, is our little alpha sunspot group, which grew over the last 24 hours quite substantially. Here's what it looked like before, and here's what it grew into. Massive growth, lots of new flux emergence throughout the whole region, and it's in an area which is overlying the existing magnetic fields. So this is a real potential volatility center, worth watching. If we look at the magnetic fields associated with it, you can see that it gets complex really quickly. Lots of opposite polarity magnetic fields all over the place. It's a veritable mess. It's been classified as a beta gamma sunspot group, but I can tell you right now that that is going to change. At least at the present time, as I look at this sunspot complex right now, it has formed multiple delta configurations. I'll show you a few of them right here. So in this area here, you can see the neutral line between the positive in white and negative in black polarities of the magnetic fields. That neutral line that separates those two separates areas of positive and negative polarity umbrae, sunspot umbrae. So this black spot here is positive in polarity, and this black spot here is negative in polarity, and they're coupled by a penumbra. This is technically a small delta region, a small magnetic delta region. Other areas are in here, this area right in here. There's a penumbra connecting these spots to these spots. At least one of these spots appears to be positive in polarity, and most of these, the rest of the spots here, are negative in polarity. If we look at the magnetogram and flash it back and forth, you can see that. And they're bridged by one single penumbra. So there is very likely a small delta configuration in this spot here, and there is a very possible developing delta here, a larger delta configuration here between these spots here and this spot here. Cycle back and forth, you can see these are positive in polarity, these spots here, and this is negative in polarity. And one final area is this spot area here. Although the penumbra hasn't quite joined up with between the two polarities, they're very, very close to joining penumbras. So one of the telltale signs that space weather forecasters use to actually analyze the volatility of a region is they look at the shape of the magnetic fields in these sunspots. I'm going to take a brief detour here and teach you a little bit about wind shear, because there's a phenomena on the Sun that's related to it. Wind shear is the change of speed or direction of wind with height. There are several different kinds of wind shear. One is directional wind shear here, where the wind changes direction with height. One is speed shear, where the velocity of the wind increases with height. And another one is speed and directional shear, where both the speed and direction of the wind changes with height. Wind shear is what actually causes tornadoes to form. It causes rotation in the atmosphere, and the shear of the wind in the atmosphere can cause that rotation to tilt until the rotation is tilted vertically and you have a tornado. On the Sun, there is a feature called magnetic shear, which plays an important role in the formation of solar flares and the release of magnetic energy. In the left-hand panel here, you see hydrogen alpha images of a sunspot complex that contain significant magnetic shear. In the right-hand side, you see a magnetogram image, just like we saw in those black and white images, but this one's a little bit different. This one shows the polarity of the magnetic fields. These colors define the strength of the magnetic field in these sunspots. These are the radially aligned fields that we see, and the blue lines represent the neutral line, or the division between the black and the white areas that we see here. So what normally happens in these active regions is these magnetic fields point perpendicular to the blue lines. So magnetic fields are moving from one area of polarity to another area of polarity, but they're following perpendicular lines at like 90-degree angles across these blue lines. And for much of this region, you can see that the lines are actually directed that way. You can see by the direction of the little black tick marks. They're going at near right angles to the direction of the blue line. Except in this area over here, they're traveling parallel to the neutral line. You see that? They're not oriented across the neutral line, they're parallel to the neutral line. That's not a good sign. That's a sign that magnetic energy is getting stored and pent up. It's called magnetic shear, and that magnetic shear is responsible for producing solar flares. Well, it's one of the components of producing solar flares. You can also see magnetic shear up here in this part where the ticks are parallel to the blue line here. This shearing action of the magnetic fields can produce oddly shaped sunspots. And one of the ways that you can tell that magnetic shear is present, or is at least influencing the situation somewhat, is when you look at a region and you can see that sunspots are not round circles. They're more line-shaped, or they're chaotic looking. They're shaped more or less this way because the magnetic fields are contorted. They're not in a stable shape. The flux that has emerged in this region over the last 24 hours has been so rapid that the magnetic fields overlying the region have not been able to respond rapidly enough, and we therefore end up with these more complex shapes of sunspots. Over time, things will sort themselves out, but probably not before solar flares occur. Solar flares occur when magnetic fields reconnect with each other, and oftentimes that reconnection stabilizes the area that produced the flare by simplifying the magnetic energy in that area. But sometimes the reconnections can actually create a more complex situation, which can further promote additional solar flares. Now, this active region over the last 24 hours was responsible for producing an M-class flare. It was a small class M1.2 solar flare, but an M-class flare is 10 times stronger than a C-class flare. So this was a notable flare. It would have actually produced a small amount of ionization in the Earth's ionosphere that would have inhibited the propagation of lower frequency radio waves, such as those used by ham radio operators, on the daylight side of the Earth only. On the night side of the Earth's ionosphere, the sun doesn't touch the ionosphere, so these effects can't be observed unless it's on the day side of the ionosphere. This region is worth watching now because it is becoming quite complex, and it is beginning to show possible delta configurations in multiple areas of the sunspot complex. It would not surprise me in the least if this region produced a major flare in the next 24 to 72 hours. It will all depend on whether or not this flux emergence continues, and if it does, how the region copes with that. At the present time, it looks like it's becoming complex quickly. I expect the magnetic classification of this region over the next 12 hours, the next time they actually analyze this region, will probably be a beta gamma delta, which is the most complex form of sunspot complex that you can have. It will again all depend on whether or not this flux emergence continues, and whether or not flares that it may produce causes simplification. This region is now more important to watch than this big boy here, because this big boy still appears to be fairly harmless. And it's more important than these sunspots over here, which are growing, but they appear to be fairly stable. If we look at the magnetic fields of these, you can see that they're still primarily in a north-south oriented direction, the neutral lines. Compare that now with our alpha sunspot, which is no longer an alpha, and you can see multiple neutral lines in various directions. And the area that concerns me probably the most is this area up in here, which is an east-west oriented neutral line. East-west oriented neutral lines, again, do not like to exist. The fact that we have fairly strong negative polarity magnetic flux up here, and it's going to try to coexist with a positive polarity flux directly south of it, is probably going to result in some fairly strong magnetic shear along this region here over time. Depends how long this flux exists for and whether or not it simplifies. Again, it's impossible to predict how this is going to pan out, but this region, out of all of the regions presently visible on the solar disk, is probably the most dangerous. So now we're going to look at the synoptic map that the space weather forecasters at the Space Weather Prediction Center have issued on the 3rd of September, which is the latest release that they've done. They've analyzed this region and have shown that the neutral line, this is the neutral line, this dotted line, for region 2673, which was the complex one we were just looking at, does appear to go east-west through that area that I mentioned just before, and then it turns south. So that's the area to watch most likely. Now, one of the things that concerns me as far as earthward directed effects go is that there is a coronal hole that is not very far away from it. Now, why is that significant? It's significant because the magnetic fields that emanate from this coronal hole go straight out into space. They do not loop back towards the sun anywhere. So if this active region produced a major solar flare that actually was capable of accelerating energetic particles like protons, those protons would quickly find their way to these open magnetic field lines and would stream out of that coronal hole towards the Earth. This is an easy avenue for high energy protons to escape from. Now, I'm teaching this to you, and I'm sure there's a lot of goofs out there who are going to misuse this information and try and elevate it into this alarming scenario. This is actually a fairly common situation, but it's something that space weather forecasters look for because this coronal hole could affect the acceleration of protons from this active region if it produced a major flare. So compare the orientation of the neutral line going through this active region with the other active regions, and you'll see what I mean by how unusual it is to have an east-west directed neutral line. This active region, as large as it is, does not have an eastward directed neutral line. The neutral line comes up the back side of the sunspot complex through the intermediate sunspots in a north-south configuration and then wraps around. This sunspot complex also appears to have a north-south directed neutral line. This sunspot complex, the line comes down here around the back side of it and then up north-south oriented through it. And then it wraps around to the next active region and again comes up in a north-south oriented direction. And these are more stable orientations. This is not. This is east-west directed, and it is not. Sunspots do not like this configuration, and they usually don't last that long. And the longer they last, usually the more prolific they are in producing solar flares. Usually, but not always. So going back to our magnetogram here, this is the area to watch. North of that primary sunspot, that's the area to really watch close, because of that east-west directed neutral line and the rapid development of flux, magnetic flux in that area. Will it produce a major solar flare in the next few days? It's really anyone's guess, but I'd say the odds are just about even now that we could see a major flare in 3 days from this region if magnetic flux continues to emerge.